Hi, it's Mr. Wagner. Well, here we are. Everything we have done this year in physics has guided us towards this moment in time. The culmination of every topic we have discussed, from velocity and acceleration to trigonometry, kinematics, forces, and Newton's laws. All of these will now be packaged together as we begin our next subject, vector resolution. We will be discussing forces in motion in not one, but two dimensions. It will require a lot of trig, a little bit of algebra, and a tremendous amount of patience. But I have the utmost faith in you, and with dedication, you will come out of this chapter having not only a better understanding of the analytical nature of physics, but a better appreciation of its relevancy in your lives. Let's get started. Let's suppose that we were given the following two vectors, A and B, and it's not important to know their magnitude and direction, just that they are not the same. If we were to add these two vectors together, we could use what's known as the head-to-tail method. This is where you take the tail of one vector and place it at the head of the second vector. Then you draw a resultant vector, which would be the sum of these two vectors combined, in this case indicated by the purple arrow. Because addition is commutative, it doesn't matter whether we were to add vector A plus B or B plus A. As you note, the resultant will be the same each time. Let's get some practice with adding actual vectors. Here I have vector A and B. We're going to add them together. Vector A is a 30 Newton force directed at 80 degrees above the horizontal, and B is a 40 Newton force directed at 30 degrees above the horizontal. To solve a vector addition problem, we must first break the vectors into their x and y components. This is the same thing as finding the opposite and adjacent sides on a triangle using trig. So as we look at this 30 Newton force at 80 degrees, we can immediately see that we have a right triangle. We can label these components the x and y components of this vector, vector A. And using a little bit of trig, we can find the values of the x and y components. The y component is 29.54, and the x component is 5.21. Now I want you to think about this. Since this is an 80-degree angle, it's no surprise that the y component is almost exactly equal to the magnitude, and the x component is much smaller. For any angle above 45 degrees, there will be a higher y component than x component. Let's now break B into its components. Using the same trig, we can determine the y and x components. The y component is 20, and the x component is 34.64. Now to add these components together and get the resultant. Here we can see that the x and y components of each will add up to give us the full resultant. And we can just set it up like this. Adding the x and y components of each of these vectors gives us the x and y components of our resultant. However, this is not our answer yet. This is just telling us these are the sides of our massive triangle now. We're just going to treat the resultant as the hypotenuse of that triangle. So to find the magnitude, we just need to use the Pythagorean theorem, where the resultant is going to be treated as the hypotenuse. So c squared is equal to x squared plus y squared, and my resultant will end up being 63.58. Now that tells me the magnitude. I still have to find the direction. Now how can I find the direction knowing just the magnitude and the sides? Well, remember you can use an inverse trigonometric function. I'm going to use inverse tangent, taking my opposite, dividing by my adjacent, and finding that my angle, theta, is 51.19 degrees. We have just resolved these vectors into their components, found the magnitude and direction of the resultant, and answered all parts of the problem. Sometimes you won't be given an angle, but a direction. North, south, east, west. And in my classroom, we treat east as 0 degrees. Now, in real navigational purposes, they often treat north as 0 degrees, but we've already established that north is up, and 90 degrees would be the equivalent of up, so we're just going to treat north as 90, south as 270, west as 180, and east as 0, and everything in between. So let's get a little bit of practice with one of these problems. A car drives 60 kilometers southwest, then 12 kilometers east. Find the magnitude and direction of the displacement. So let's just draw out a free body diagram to show what's going on here with our compass directions labeled. We have 60 kilometers southwest. Now, remember, west is 180 degrees and south is 270 degrees. So that means that our angle is in between these two, since it's southwest. 45 degrees below west would be 225 degrees. So our vector is directed at 225 degrees and has a magnitude of 60 kilometers. Let's again resolve this vector into its components, x and y. And when we do that, using trig, we find that the x and y components are equal. After all, this is a 45-45-90 triangle, so it's no surprise that they are equal. Please also note they are negative. And we would expect that to be the case, because we are in the third quadrant, where both our x and y values will be negative. Okay, for the 12-kilometer east vector, that one's fairly straightforward, no pun intended, because this is going to be simply an x component of 12 and a y component of 0, because the sine of 0 is 0, and the cosine of 0 is 1. 1 times 12 is 12. So now we have to resolve these vectors. I'm just drawing them out here as the compass would show, but remember, we have to go head to tail. It's a really good practice whenever you do these problems to sketch out your vectors. That way you have an idea what quadrant they're going to be in and whether your answer is going to be positive or negative. And that's what I've done here. And you can see that the resultant is still going to be in the third quadrant. So now I'm going to put these components together and find my resultants. And we can kind of see what's going on here with the x and y component of A and also the x component of B, which is the vector itself. There is no y component. And we see the resultants components will, again, both be negative. And the magnitude of this we can find with the Pythagorean theorem, where the resultant squared is equal to x squared plus y squared, and the resultant is 52.21. To find the direction, now this is a little bit complicated. You still can use inverse sine, but you have to keep in mind, what are you actually finding? You are finding the deviation of this vector from the vertical, and that is shown here. So once we solve this problem and use our inverse tangent function, we find that theta is 35.64. Now, that is implying that the answer should be in the first quadrant. But you have to ask yourself, what is this for 35.64 from? That is the deviation from the vertical axis, or in this case, south. Since we are talking about directions on the compass, this is a deviation of 35.64 degrees west of south, and this is an acceptable answer. If you had to find an actual angle instead of a direction, you could just take 270 degrees, which is south, and subtract this value, 35.64, from it to get an actual direction of 234.36 degrees. But again, this is an acceptable answer for the problem. So using trig and algebra, we can resolve vectors into their components and use those to solve problems. Or, given component forces, we can combine them to determine a resultant. Complete the worksheet on Classroom and have a wonderful day.